quiet place where curiosity slows its breathing and complicated ideas are allowed to unfold without urgency. This is a space for wandering thoughts, for gentle explanations, and for questions that don't demand immediate answers. Tonight, we're turning our attention downward, far below the familiar surface of things, toward a place that almost never appears in daily life, yet has a strange way of unsettling even the most experienced scientists. The topic waiting for us is the Mariana Trench, the deepest known part of Earth's oceans. It's often described with numbers that sound impressive but distant, measurements that are hard to feel in the body. Nearly 11 kilometers down, deeper than Mount Everest is tall, far beyond the reach of sunlight. But none of those facts quite explain why this place continues to inspire unease, caution, and, in some cases, genuine fear among the people who study it for a living. There's something about the idea of depth that behaves differently from height. Looking up at a tall mountain or a high building can feel exhilarating, even empowering. The sky is open, the air feels generous. But looking down into deep water triggers a very different response. The surface may be calm, even beautiful, yet the knowledge of what lies beneath introduces a subtle tension. The mind starts to fill in gaps. The imagination grows active, and the deeper the water gets, the less reliable those imagined pictures become. The Mariana Trench isn't frightening because of monsters or myths, at least not in the usual sense. It's frightening because it exists beyond almost every boundary the human body relies on. No breathable air, no natural light. Pressure's so intense that ordinary materials crumple as if they were made of paper. Temperatures hovering just above freezing. And perhaps most unsettling of all, the near certainty that almost everything down there happens without witnesses. Scientists are trained to be comfortable with uncertainty. They spend their lives measuring what they don't yet understand, refining models, revising assumptions, and learning to sit patiently with incomplete information. And yet, when it comes to the deepest parts of the ocean, even seasoned researchers tend to speak more carefully. Their language becomes precise, sometimes hesitant. Not because they lack data entirely, but because the environment itself resists easy explanation. Before we drift any farther, let me gently pause to ask you something. Where are you listening from right now? Are you somewhere quiet, maybe preparing to rest? Or are you letting this play softly in the background while the day winds down? And what time is it in your part of the world at this very moment? It's a small detail, but somehow fitting. A story about a place untouched by clocks, schedules, or daylight, being heard at countless different hours across the planet. If you find this kind of slow, thoughtful exploration calming or simply interesting, you're always welcome to support this little corner of the internet by liking the video or subscribing. It helps these long, unhurried conversations reach others who might appreciate a quieter approach to science and the unknown. There's no rush though. Nothing here needs to be done quickly. Now, when people first hear about the Mariana Trench, their curiosity often follows a familiar path. How deep is it exactly? What lives there? Has anyone been to the bottom? Those are natural questions, and we'll get to them in time. But the fear scientists feel isn't rooted in a lack of bravado or courage. It comes from a recognition of scale and indifference. The trench does not react to human presence. It does not accommodate mistakes. It does not offer second chances easily. Imagine standing on a ship in the open Pacific Ocean. The horizon forms a smooth, unbroken circle. The water reflects the sky so well that it's sometimes hard to tell where one ends and the other begins. Beneath that surface, though, the seafloor slopes downward gradually at first, like a continental shelf easing into deeper water. Then, without warning, it drops away into a vast, narrow wound in the Earth's crust. That drop continues for miles, long after any light from the surface has been swallowed. What makes this unsettling for scientists is not simply the depth, but the isolation. Space is often described as hostile, yet it has one advantage oceans do not. When something goes wrong in space, there is usually time to notice. Pressure changes are dramatic but detectable. In the deep ocean, pressure increases steadily and relentlessly. There is no threshold where it suddenly becomes dangerous. It is dangerous almost immediately, and then it becomes catastrophic. For most of human history, the deep ocean was not something people worried about. It existed as an abstract idea, a dark counterpart to the land. Sailors feared storms, reefs, and shipwrecks, not the water itself. Even early scientists had little reason to think about what lay thousands of meters below. Nets reached only so far. Light disappeared quickly. Out of sight became out of mind. That changed slowly, and then all at once. As technology improved, instruments began to probe deeper than any human ever could. Echoes returned from unfathomable distances. Seafloor maps revealed shapes no one expected to find. Instead of a smooth, muddy bottom, there were mountains, valleys, and trenches that rivaled anything on land. The Earth, it turned out, was far more textured beneath the waves than anyone had imagined. The Mariana Trench stands out even among these discoveries. It isn't just deep, it is sharply defined, narrow, and extreme. It marks a place where one tectonic plate slides beneath another, dragging surface material down into the mantle. This process is slow, steady, and unstoppable on human timescales. The trench is not a static feature. It is an ongoing action frozen into geography. For scientists, this raises uncomfortable questions. What happens to matter under that much pressure for that long? How do chemical reactions behave when squeezed beyond laboratory conditions? How does life adapt, not temporarily but permanently, to an environment that would instantly destroy almost everything familiar? Fear, in this context, doesn't look like panic. It looks like caution. It looks like double-checking calculations. It looks like designing equipment with absurd safety margins and still worrying that it won't be enough. It looks like acknowledging that, even with decades of progress, the deep ocean remains one of the least forgiving places we can choose to explore. There is also a quieter fear, one that doesn't often make it into academic papers. It's the realization that, despite all our satellites and sensors, despite global communication networks and advanced models, there are places on our own planet where we are still visitors at best. Not explorers in the heroic sense, but temporary intrusions, dependent on fragile machines and constant support from the surface. The Mariana Trench reminds scientists that knowledge has limits, and those limits are not always pushed back by enthusiasm alone. Sometimes they are held in place by physics, chemistry, and biology, acting together in ways that are simply incompatible with human life. And yet, the trench keeps drawing attention, not because it promises easy answers, but because it sits at the intersection of so many unanswered questions about Earth's formation, about the resilience of life, about the boundaries of technology, about how much of our fear comes from real danger, and how much comes from confronting environments that do not acknowledge us at all. As we continue, the focus will slowly narrow, from the broad idea of depth and unease toward the specific conditions that make this place so challenging. The numbers will become more tangible, the stories more concrete, the reasons for that lingering scientific dread more understandable, not through exaggeration, but through accumulation. For now, just let the image settle, a calm ocean surface, a depth below it that refuses to be imagined all at once, and a quiet understanding that some parts of our world remain profoundly uninterested in being known, even as we keep trying. The ocean has a way of disguising its most dramatic features. From the surface, especially on a calm day, it can look almost flat, even gentle. The waves roll, the light dances, and everything about it suggests continuity, as if the water below is simply more of the same, but that impression fades quickly once you start thinking vertically instead of horizontally. The greatest drop on the planet doesn't announce itself with cliffs or warning signs. It begins quietly, beneath ships that pass overhead without ever sensing what lies below them. The deepest known place in the ocean is the Mariana Trench, and what makes it so unsettling to scientists isn't only how far down it goes, but how quickly the world changes as you descend toward it. This is not a gradual fading into darkness in the way twilight slips into night on land. In the ocean, light gives up in stages, each one stripping away something fundamental that life at the surface depends on. At the very top, sunlight still rules. Waves scatter it, bend it, fracture it into shifting patterns, but it is present. Colours exist. Motion is easy to see. This is the part of the ocean most people recognise, whether from beaches, boats, or photographs. It feels alive in a familiar way. Fish dart through illuminated water. Algae and plankton convert light into energy. Everything here is driven by the same star that governs life on land. But light does not travel far in water. Even in the clearest tropical seas, it weakens rapidly. Within the first couple of 100 meters, reds and yellows vanish. Objects take on a bluish cast. Shadows soften. For scientists, this is the first signal that the environment is becoming something else entirely. Vision, one of the primary tools humans rely on, begins to lose its usefulness. As the descent continues, the changes accelerate. The sunlit zone gives way to dimness. Photosynthesis becomes impossible. Plants, as we know them, can no longer survive. This boundary is not marked by a sharp line, but by a slow surrender. Less energy enters the system. Food becomes scarcer. Life adapts or disappears. By the time you reach what scientists call the twilight zone, the ocean feels fundamentally altered. Light still exists, but it no longer behaves the way we expect. It arrives faintly, scattered, stripped of warmth. Shapes are harder to distinguish. Movement becomes ambiguous. Many organisms here rely on senses other than sight, or develop eyes so sensitive they would be overwhelmed at the surface. For researchers, this zone already presents challenges. Instruments must function with limited visibility. Cameras need artificial light, which alters animal behavior. Even defining what counts as day or night becomes complicated because the difference is subtle at best. Yet this is still only the beginning of the descent. Below the twilight zone lies true darkness, not the darkness of a moonless night, where stars still provide reference points, but an absence of sunlight altogether. At these depths, no photon from the sun has ever reached. The ocean becomes a place governed by pressure, chemistry, and time rather than by light-driven cycles. This is where the psychological unease begins to deepen for scientists. Darkness removes context. Without visual cues, it becomes harder to judge distance, scale, or motion. A camera's field of view is limited to whatever its lights can illuminate, creating the impression of floating in an endless void. Beyond that illuminated bubble, there is nothing visible at all. As the seafloor drops away toward the trench, the sense of vertical distance becomes abstract. On land, even the deepest canyons provide walls, textures, and reference points. In the open ocean, especially over a trench, there may be kilometers of uninterrupted water column beneath you. No landmarks, no gradual slopes you can see, just depth. The Mariana Trench takes this to an extreme. It is not merely deep, it is sharply defined. The surrounding seafloor plunges downward into a narrow, elongated depression. This shape matters because it concentrates pressure and isolates the environment even further. Water trapped at the bottom circulates slowly. Changes occur over immense timescales. For scientists, the loss of light is not just an aesthetic issue. It reshapes every biological and chemical process. Without sunlight, there is no photosynthesis. That means no plants forming the base of the food web. Instead, life depends on organic matter drifting down from above, or on chemical energy sources released from the Earth itself. This creates an ecosystem that is both fragile and resilient in unexpected ways. Fragile because energy input is limited and irregular. Resilient because the organisms that survive here are adapted to conditions that would kill almost anything else. Understanding this balance requires careful observation, but observation itself is difficult when darkness is absolute. Human perception struggles in such environments. Our brains evolve to process visual information constantly. When vision fails, imagination fills the gaps. For scientists descending into these depths via remotely operated vehicles or crewed submersibles, the experience can be disorienting even when viewed through screens. There is a persistent awareness that beyond the camera's light lies an immeasurable volume of unseen water. As depth increases, another invisible factor becomes impossible to ignore. Pressure rises relentlessly. For every 10 meters of descent, pressure increases by roughly 1 atmosphere. By the time you reach the bottom of the Mariana Trench, the pressure is more than 1,000 times what it is at sea level. This pressure doesn't announce itself with sound or movement, it simply exists, constant and crushing. The combination of darkness and pressure is particularly unsettling. In darkness alone you might imagine movement. In pressure alone you might imagine compression. Together they create an environment where mistakes are unforgiving. A small crack in equipment, insignificant at the surface, becomes catastrophic at depth. Materials behave differently. Electronics fail in unexpected ways. Seals that held perfectly during testing may deform over time. This is one reason scientists speak about the trench with such respect. It is not a place where redundancy feels optional. Every system must work not just once, but continuously, without the possibility of repair. When something goes wrong at those depths, recovery is often impossible. The loss of light also removes the familiar rhythm of time. On land, day and night provide structure. In shallow water, that rhythm persists. In the deep ocean, it disappears. There is no sunrise, no sunset, no gradual change in illumination. Conditions remain the same hour after hour, year after year. This timelessness affects life in subtle ways. Many deep-sea organisms have no circadian rhythms as we understand them. Others respond to cues we barely recognize, such as faint vibrations or chemical gradients. For scientists trying to study behavior, this presents a challenge. Observations made during one visit may not generalize easily, because activity cycles may be slow or irregular. Even defining here becomes tricky. When researchers lower instruments into the trench, they rely on depth measurements and coordinates, but the environment itself offers few distinguishing features. One section of the trench can look much like another, especially in darkness. Mapping becomes an exercise in patience and precision. There is also the unsettling realization that light, something we often associate with safety and understanding, is completely absent here. Everything scientists know about the deepest parts of the trench comes from indirect measurements, brief visits, and limited samples. The darkness is not just physical, it is informational. This feeds into a broader discomfort. The deepest drop in the ocean represents a boundary where human intuition fails. Concepts like down and bottom lose clarity when pressure increases without visible change. The ocean does not behave like a solid landscape. It is a fluid column that hides its extremes beneath a deceptively uniform surface. Scientists often compare the deep ocean to outer space, but the analogy is imperfect. Space is empty in a way the ocean is not. Water transmits sound efficiently. It exerts force continuously. It infiltrates even the smallest gaps. In darkness, these qualities become more noticeable. Every movement creates pressure waves. Every vibration travels far. When submersibles descend toward the trench, researchers monitor not just depth, but temperature, salinity, and pressure gradients. These data streams tell a story of a world stratified by physics. Each layer behaves differently. Light disappears early, but other changes continue long after. The knowledge that the deepest drop on Earth lies hidden beneath so much water is unsettling in part because it contradicts everyday experience. On land, depth is something you can usually see. You can look down into a canyon, you can judge a cliff. In the ocean, depth is concealed. The surface gives nothing away. This concealment feeds fear, not the kind that causes panic, but the kind that demands caution. Scientists know that environments which hide their extremes often punish assumptions. The Mariana Trench does not reward overconfidence. It requires humility, patience, and acceptance of uncertainty. As research continues, instruments become more capable, cameras grow more sensitive, materials become stronger, yet the fundamental conditions remain unchanged. Light will not reach the bottom. Pressure will not ease. The trench remains a place defined by absence as much as by presence. Understanding where the light gives up is the first step in understanding why this place remains so intimidating. Darkness here is not a temporary condition. It is permanent. It shapes every process, every adaptation, and every risk. And as scientists continue their descent, both literally and figuratively, the realization settles in that the greatest drop on Earth is not just a measurement, but a boundary between the familiar and the profoundly alien. From this point downward, the ocean becomes less forgiving, less accessible, and more demanding of precision. What lies beyond is not revealed all at once, but slowly, under conditions that test both technology and patience. And as the depth increases, so does the awareness that the absence of light is only one of many thresholds still ahead. Long before anyone knew where the deepest point on Earth was, the ocean floor existed mostly as an idea. It was assumed to be distant, muddy, and largely unremarkable, a flat extension beneath the waves that mattered only insofar as it supported the surface above. For centuries, humans crossed oceans without ever truly considering what lay beneath their hulls. Depth was something sailors measured only to avoid running aground. Beyond that practical concern, the seafloor might as well have been another planet. The discovery of what we now call the Mariana Trench did not happen because someone set out specifically to find the deepest place on Earth. It emerged slowly, almost reluctantly, as a byproduct of curiosity, improved instruments, and the gradual realization that the planet was far more uneven than early science had assumed. What unsettled scientists later was not just how deep this place turned out to be, but how long it remained hidden in plain sight beneath the world's largest ocean. In the early days of ocean exploration, depth measurement was an exercise in patience and approximation. Sailors used weighted ropes or lines, lowering them until they hit the bottom. These methods worked reasonably well in shallow coastal waters, but they failed quickly as depth increased. Lines drifted. Currents pulled them at angles. Ropes stretched under their own weight. At great depths, it became difficult to tell whether the weight had actually reached the bottom or was simply suspended in the water column. As a result, early depth charts were sparse and misleading. Vast regions of the Pacific were marked with vague notations or left blank altogether. The ocean floor was imagined as a broad, gently sloping basin, deep in places but fundamentally simple. There was no strong reason, at the time, to suspect otherwise. The shift began in the 19th century, during a period when scientific expeditions started to treat the ocean as something worth studying in its own right. One of the most influential of these voyages was undertaken by a British research ship equipped with instruments designed not just for navigation, but for systematic observation. This expedition marked one of the first attempts to map the deep ocean scientifically, rather than incidentally. When researchers began lowering weighted lines into the Pacific during this era, they encountered something unexpected. In certain regions, the lines kept going, and going, and going. Measurements returned depths that far exceeded anything previously recorded. At first, these readings were treated with skepticism. Instruments could fail, lines could snap, errors were common, extraordinary claims required extraordinary verification. Still, as more measurements accumulated, a pattern began to emerge. In the western Pacific, near a chain of islands, the ocean floor did not behave as expected. Instead of levelling off, it plunged downward in a long, narrow depression. The data hinted at a feature unlike anything previously documented, something deeper and more sharply defined than the surrounding seafloor. Even then, it took time for the significance of this discovery to sink in. Early measurements lacked precision. Depth estimates varied widely. The idea that Earth contained a trench deeper than the tallest mountains were high was difficult to reconcile with existing geological models. Some scientists proposed that the readings were anomalies. Others suggested errors in calculation or equipment. What gradually tipped the balance was repetition. Independent measurements, taken years apart, began to converge. Different expeditions reported similar extreme depths in roughly the same region. The ocean, it seemed, had been quietly hiding its most dramatic feature beneath thousands of meters of water. As the 20th century approached, technological advances began to change the picture more decisively. The introduction of echosounding, which uses sound waves to measure distance, revolutionized seafloor mapping. Instead of relying on physical lines, ships could send sound pulses downward and measure the time it took for echoes to return. This method was faster, more reliable, and capable of reaching depths that had previously been impractical. When echo sounding was applied systematically across the Pacific, the results were striking. The seafloor was revealed as a complex landscape of ridges, plains, and trenches. The deepest of these stood out clearly, carving a long, sinuous scar into the Earth's crust. The Mariana Trench was no longer a vague suspicion. It was a measurable, repeatable feature. Yet even with improved tools, understanding what this trench represented took time. Depth alone did not explain its existence. Why here? Why so deep? Why so narrow? These questions push scientists beyond simple mapping and into the realm of geology and planetary processes. The emerging theory of plate tectonics provided a framework that finally made sense of the trench's origin. Earth's surface, rather than being a single continuous shell, is broken into massive plates that move slowly over geological time. Where these plates collide, one can be forced beneath another, sinking into the mantle in a process known as subduction. The Mariana Trench marks such a boundary. where one plate is being dragged downward, carrying surface material with it into the depths. This explanation was elegant, but it also introduced new discomfort. The trench was not a static feature left over from some ancient event. It was active, slow by human standards, but relentless on geological timescales. The seafloor was still moving, still deforming, still changing shape far below the surface. For scientists, this realization reframed the trench from a curiosity into a dynamic system. Studying it was no longer just about measuring depth. It became a way to observe Earth's internal processes in action. But observing those processes directly remained difficult, because the trench was and remains extraordinarily hard to access. Even as sonar mapping improved, direct exploration lagged behind. Sending instruments into the trench required engineering solutions that did not yet exist. Pressure-resistant materials were expensive and difficult to work with. Communication through kilometers of water was unreliable. Retrieval of equipment was risky, often unsuccessful. This gap between knowledge and access contributed to the trench's unsettling reputation. Scientists could map it, model it, and theorize about it, but they could not easily visit it. Much of what was known came from indirect evidence, which always carries a degree of uncertainty. When the first crude descents finally occurred, they did not dispel this unease. Instead, they deepened it. Reaching the bottom confirmed the extreme pressures and darkness predicted by theory, but it also revealed details that raised new questions. The seafloor was not lifeless. Sediments behaved strangely under pressure. Human debris, carried by currents, had found its way even to these depths. The fact that the deepest place on Earth could still be influenced by surface activity was disturbing in a different way. It suggested that isolation was not absolute, that no part of the planet was entirely beyond reach, for better or worse. The process of discovering the trench also highlighted how incomplete our understanding of the oceans remains. Even today, large portions of the deep seafloor are mapped at relatively low resolution compared to the surfaces of the Moon or Mars. The irony is not lost on scientists. We have detailed images of distant planets, yet our own planet's depths remain only partially explored. This incomplete picture feeds scientific caution. Every new discovery in the trench has the potential to revise existing models. Depth estimates have been refined repeatedly as instruments improve. The exact shape of the trench continues to be updated. Even its deepest point has been remeasured multiple times, with small but meaningful differences. These refinements matter because they affect how scientists interpret everything from seismic activity to ocean circulation. The trench is not just a hole. It is a boundary where Earth's interior and surface interact. Understanding it requires precision, and precision is difficult to achieve under such extreme conditions. The story of how the trench was discovered is therefore not one of sudden revelation, but of gradual accumulation. Each measurement added a piece to the puzzle. Each technological improvement sharpened the image. And with each step, the realization grew that the ocean was not hiding something small or incidental, but something vast and fundamental. For researchers, there is a humbling lesson in this history. The deepest scar on Earth was always there, shaping tectonic forces and influencing the planet's structure. Humans simply lacked the tools and perhaps the perspective to notice it. Its discovery was as much about changing how we look as about finding something new. This sense of humility persists in modern trench research. Scientists approach the area knowing that surprises are likely. Models are treated as provisional. Data is scrutinized carefully. The environment does not forgive assumptions easily. As exploration continues, the trench remains a reminder that discovery does not always bring comfort. Sometimes it reveals complexity where simplicity was assumed. Sometimes it exposes scales that resist intuition, and sometimes it leaves us with a clearer map but deeper questions. From here, the focus naturally shifts from finding the trench to confronting what it does to anything that enters it. Depth is not just a number. It has physical consequences that become impossible to ignore as pressure mounts and conditions diverge further from the surface world. And as scientists learned soon after locating this deeper scar, knowing where it is only marks the beginning of understanding what it demands. By the time scientists had confirmed the location and depth of the world's deepest trench, one truth became impossible to soften or reinterpret. The problem was not distance alone, it was pressure. Distance can be crossed with patience and fuel. Pressure is different. Pressure does not negotiate. It accumulates silently, evenly, and without mercy, turning the surrounding environment into something fundamentally incompatible with the human body. At the surface of the ocean, pressure feels unremarkable because it is familiar. The atmosphere presses down with a steady weight, one that human bodies have evolved to tolerate so completely that it disappears into the background of everyday life. Lungs inflate easily. Blood circulates normally. Materials hold their shape. Nothing about the environment demands constant attention. The moment descent begins, that balance starts to shift. With every meter downward, the weight of water above increases. Unlike air, water does not compress easily, which means its mass stacks relentlessly. Pressure rises not in dramatic jumps, but in a smooth mathematical progression. There is no warning moment where things suddenly become dangerous. Instead, conditions quietly pass thresholds that the human body and human-made materials were never designed to cross. By the time you reach a depth of just 10 meters, the pressure has already doubled compared to sea level. At 30 meters, it has quadrupled. For divers, these changes are manageable only because of specialized training, equipment, and strict limits on time spent at depth. Even then, the risks are significant. Nitrogen dissolves into tissues, gases behave differently, small mistakes can lead to injury or death, and yet these depths represent only the shallowest fringe of the ocean. They are insignificant compared to what lies below. As descent continues into hundreds, then thousands of meters, pressure increases to levels that no unprotected human body could survive for even a moment. Lungs would collapse, blood chemistry would destabilize, cavities within the body would compress violently. Survival becomes physically impossible, not because of lack of oxygen alone, but because the body itself ceases to function as a coherent structure. At the bottom of the Mariana Trench, pressure exceeds 1,000 atmospheres. This is not an abstract figure. It means that every square centimetre of surface area is bearing the weight of roughly a metric ton of force. Every joint, every seam, every microscopic flaw is subjected to constant compression. Nothing is spared. Nothing is shielded. Scientists often compare this pressure to having a mountain stacked on top of you, but even that metaphor struggles to convey the reality. A mountain exerts its weight unevenly, concentrated downward through gravity. Deep-sea pressure comes from all directions at once. It is perfectly uniform, pressing inward from every angle, seeking any weakness it can exploit. This is why humans do not simply build thicker suits and descend. The problem is not insulation. It is structural integrity. The human body relies on internal pressure differences to function. Lungs depend on expandable spaces. Blood vessels depend on elasticity. Cells depend on membranes that maintain delicate balances. Extreme pressure disrupts all of this simultaneously. Even rigid materials struggle. Steel deforms, glass shatters, plastics creep and warp over time. Engineers designing submersibles must account not just for immediate compression, but for long-term fatigue. A hull that survives one descent may fail on another due to microscopic damage accumulated under stress. This reality shapes every aspect of deep-sea exploration. Crude submersibles are built around pressure-resistant spheres, often made of thick titanium or specially treated steel. These spheres are designed to distribute stress evenly, minimizing weak points. Windows are tiny, not because visibility is unimportant, but because openings are liabilities. Every penetration through the hull introduces risk. Even with these precautions, the margin for error remains slim. At such depths, a failure does not unfold gradually. It is instantaneous. A breach the size of a coin can lead to catastrophic collapse in milliseconds. There is no opportunity for escape, no time for correction. The physics simply takes over. For scientists, this creates a constant background tension. Exploration at extreme depth is not just a technical challenge, it is a negotiation with forces that do not forgive optimism. Every mission involves calculations that err on the side of conservatism. Every design decision reflects lessons learned from failures, some of them fatal. The pressure environment also complicates scientific instruments. Sensors must be encased, electronics must be isolated, fluids used in hydraulic systems must remain stable under compression. Even simple mechanical components behave differently when subjected to thousands of atmospheres. Lubricants thicken, springs lose elasticity, materials that are perfectly reliable at the surface become unpredictable. This makes data collection slower and more deliberate. Instruments are tested repeatedly under simulated conditions. Pressure chambers recreate the forces expected at depth, allowing engineers to observe how systems respond. Yet simulations can never capture every variable. The ocean introduces temperature gradients, salinity differences, and dynamic forces that are difficult to replicate perfectly in a laboratory. The psychological weight of this knowledge affects how scientists approach the trench. There is respect, bordering on wariness, not because the environment is hostile in a personal sense, but because it is indifferent. The trench does not react to human presence. It does not become more forgiving with experience. It simply exists, governed by physical laws that remain constant. Pressure also shapes the biology of the trench in ways that challenge intuition. Life at these depths is not crushed because it evolved under these conditions from the beginning. Cellular structures are adapted to withstand compression. Proteins function differently. Membranes maintain stability where surface-dwelling organisms would fail. These adaptations are precise, not generalized. They reflect millions of years of evolution under conditions that humans can only briefly intrude upon. This contrast reinforces the sense that humans are visitors in an environment that does not belong to them. Even the most advanced submersible is an artificial bubble, a fragile pocket of surface conditions carried into a place where those conditions are fundamentally alien. Pressure also imposes limits on time. Even if a submersible remains structurally sound, missions are constrained by battery life, communication delays, and the sheer complexity of operating systems under stress. Descents and ascents take hours. Every moment at depth is carefully planned. There is little room for improvisation. For uncrewed vehicles, the risks are somewhat different but no less significant. Remotely operated vehicles and autonomous systems must be able to withstand pressure without the benefit of human oversight on site. Failures can result in the permanent loss of expensive equipment and irreplaceable data. Recovery from extreme depth is often impossible. These losses are not hypothetical. Throughout the history of deep-sea exploration, instruments have been crushed, lost, or rendered inoperable. Each incident adds to a collective understanding of what pressure can do, but it also reinforces the sense that the trench demands humility. The idea that humans do not belong at such depths is not a judgment. It is an observation grounded in physics and biology. Our bodies evolved in a narrow band of pressure conditions near the surface. Our technologies extend that range only slightly, and always at great cost and risk. This does not mean exploration is futile. On the contrary, the fact that humans can reach these depths at all is a testament to ingenuity. But it does mean that every descent carries an implicit acknowledgement of vulnerability. The trench is not conquered by presence, it is temporarily endured. As research continues, pressure remains the defining constraint. It shapes mission design, limits frequency, and influences the kinds of questions scientists can realistically ask. It forces prioritization. What data is worth the risk? What samples justify the expense? What uncertainties can be tolerated? The answers to these questions evolve, but the underlying reality does not. Pressure at the bottom of the Mariana Trench will always be immense. It will always exceed what humans can withstand unaided. It will always demand respect. Understanding this helps explain why fear persists, even among experts. It is not fear of the unknown in a vague sense. It is fear grounded in precise numbers, material limits, and hard-earned experience. It is the awareness that one miscalculation, one overlooked flaw, can be final. And as scientists continue to push the boundaries of exploration, this awareness travels with them, shaping every decision. Pressure is not just a physical force in the trench. It is a constant presence in the minds of those who study it, a reminder that some environments allow no margin for error, and that knowing where humans do not belong is as important as knowing where they do. When sunlight disappears completely, life does not politely follow it into extinction. That is perhaps the most unsettling truth scientists uncovered as they began to explore the deepest parts of the ocean. Logic once suggested that without light, ecosystems would collapse. No photosynthesis, no plants, no base for food webs. And yet, in the permanent midnight of the deep sea, life persists, adapts, and in some cases thrives in ways that feel almost defiant. The depths of the Mariana Trench exist in a state that never changes with the time of day. There is no dawn creeping in from the horizon, no dusk signalling rest, no seasonal variation in brightness. Darkness is not a phase here. It is the environment itself. Every organism born in this place has never experienced light and never will. For humans, darkness is usually temporary. Even the longest night carries the promise of morning. That expectation shapes how we think, how we rest, and how we measure time. In the trench, that framework collapses. There is no visual rhythm to anchor behavior. Life must rely on entirely different cues to survive. Scientists once assumed that deep-sea life would be sparse and sluggish, existing at the bare minimum required to persist. Energy is limited after all. Organic material drifts down slowly from the surface, arriving in fragments and pulses. Sometimes a dead whale sinks, delivering a sudden feast. Other times weeks or months pass with very little input. This unpredictability forces organisms to be efficient, patient, and opportunistic. What surprised researchers most was not just that life existed, but how specialized it was. Many trench-dwelling organisms have bodies that appear fragile, almost translucent. This is not weakness, it is adaptation. Dense skeletons are unnecessary and even disadvantageous under extreme pressure. Soft tissues compress evenly, avoiding the structural failures that rigid materials suffer. Eyes, when present at all, are often reduced or modified beyond recognition. Vision serves little purpose in complete darkness. Instead, other senses dominate. Some species detect minute changes in water pressure. Others sense chemical traces left behind by passing organisms. Sound and vibration travel efficiently through water, and many deep-sea creatures are exquisitely sensitive to these signals. One of the most striking adaptations to permanent darkness is bioluminescence. In the absence of sunlight, some organisms produce their own light through chemical reactions within their bodies. This light is not decorative, it is functional. It can lure prey, confuse predators, or facilitate communication in an environment where visibility is otherwise non-existent. For scientists observing these organisms through submersible cameras, bioluminescence introduces a strange contradiction. The trench is dark, yet it flickers with sudden points of light, brief and purposeful. These flashes are reminders that life here follows rules that feel alien but are internally consistent. Food webs in the trench are built on scarcity. With no plants to convert light into energy, life depends on what sinks from above or on chemical processes tied to the Earth itself. Organic debris, often called marine snow, drifts downward constantly. It consists of dead plankton, fecal pellets, and fragments of larger organisms. By the time it reaches the trench, much of its energy has already been stripped away. Some organisms have adapted to extract every possible nutrient from this meagre supply. They eat slowly. They grow slowly. Their metabolisms are tuned to conservation rather than speed. Others take advantage of sudden windfalls. A large carcass falling into the trench can support a localized ecosystem for years, attracting scavengers from miles away. There are also communities that rely on chemosynthesis rather than photosynthesis. In certain areas, chemical reactions driven by geological processes release energy-rich compounds into the surrounding water. Specialized bacteria use these compounds to produce organic matter, forming the base of food chains entirely independent of sunlight. This discovery challenged long-standing assumptions about the limits of life. It suggested that sunlight, while crucial for surface ecosystems, is not the only viable energy source. Life can persist wherever there is a stable gradient to exploit, whether that gradient is light, chemistry, or pressure. For scientists, this realization carries implications far beyond the trench. It informs discussions about life on other planets and moons, particularly those with subsurface oceans hidden beneath ice. If life can exist in permanent darkness under immense pressure on Earth, similar environments elsewhere may also be viable. Still, studying trench life remains extraordinarily difficult. The organisms are fragile when brought to the surface. Pressure changes alone can destroy cellular structures. Many species cannot survive decompression. making long-term laboratory study nearly impossible. What scientists observe is often limited to brief encounters captured on video or through carefully preserved samples. This limitation introduces uncertainty. Behavior observed during a short visit may not reflect normal activity. Artificial lights alter responses. Noise from submersibles may cause avoidance or attraction. Every data point must be interpreted cautiously, with an awareness of how intrusive the observation itself may be. There is also the unsettling fact that some trench organisms have been found to contain pollutants, originating from human activity. Chemicals and microplastics have been detected even at the deepest depths. This discovery undermines the notion of the trench as a pristine refuge untouched by surface processes. Darkness does not equal isolation. For scientists, this is deeply troubling. It means that even in permanent midnight, human influence reaches. Currents carry contaminants downward. Particles sink. Time ensures eventual arrival. The trench records not only natural history but industrial history as well. Life in the trench also challenges how scientists define resilience. These organisms survive extremes of pressure and darkness, yet they may be highly sensitive to subtle changes in chemistry or temperature. A small shift in conditions could have outsized effects. The stability of permanent midnight is deceptive. It feels unchanging, but it depends on delicate balances maintained over long timescales. The absence of sunlight also alters reproduction and development. Many trench organisms have long lifespans and low reproductive rates. Offspring may drift for extended periods before settling. Survival depends on timing that cannot be synchronized to day or season in any familiar way. From a human perspective, this kind of existence is difficult to imagine. No light to mark beginnings or endings, no visual cues to anchor memory. Yet life here is not impoverished. It is simply different, adapted to constraints that surface life never encounters. Scientists studying this environment often speak with a mix of fascination and unease. Fascination at the ingenuity of evolution, unease at how little margin exists for disturbance. When an ecosystem is built on scarcity and stability, disruption can ripple outward unpredictably. The trench forces researchers to confront the idea that darkness is not emptiness. It is a condition under which life reorganizes itself around entirely different priorities. Energy efficiency replaces abundance. Sensory perception replaces vision. Patience replaces speed. As exploration continues, each new observation adds to a growing picture of an ecosystem that operates without sunlight yet remains intricately structured. Understanding this structure requires time, caution, and respect for the limitations imposed by the environment. And as the descent continues, beyond the known communities and into even greater depths, the question becomes less about whether life exists and more about how far adaptation can be pushed before even evolution reaches its limits. There is a moment that many scientists remember clearly when they first review footage from the deepest parts of the ocean. It usually happens quietly, long after the expedition itself is over, sitting in front of a screen, watching grainy images recorded under impossible conditions. At first there is darkness broken only by the cone of artificial light. Then something moves, slowly, deliberately. And the realization settles in that what is moving should not, by conventional understanding, be there at all. In the Mariana Trench, life does not merely survive. It violates expectations that once felt fundamental. For decades, textbooks suggested clear boundaries for where complex life could exist. Pressure limits, temperature limits, energy limits. Yet the trench repeatedly ignores these boundaries, presenting organisms that appear fragile, almost unfinished, and yet function perfectly within conditions that destroy most human technology. The phrase "shouldn't exist" is not an exaggeration born of drama. It reflects how thoroughly these creatures defy assumptions based on surface biology. Under pressures exceeding 1,000 atmospheres, protein should misfold, cell membranes should collapse, chemical reactions should behave unpredictably, and yet life persists in forms that not only endure these conditions but depend on them. One of the most frequently encountered animals in the trench is a type of amphipod, a small crustacean-like creature that resembles a translucent shrimp. At first glance, it looks unremarkable, soft-bodied, pale, almost delicate. But this apparent fragility is deceptive. Amphipods thrive at depths where vertebrates struggle to survive even briefly. They scavenge efficiently, reproducing in an environment where food is scarce and pressure is crushing. Scientists analysing these amphipods discovered biochemical adaptations that seemed almost counterintuitive. Their cellular membranes contain specific compounds that remain stable under extreme pressure. Their enzymes are structured in ways that allow chemical reactions to proceed normally, despite compression. These are not minor tweaks. They are fundamental redesigns at the molecular level. Then there are the snailfish, a group that became emblematic of trench life precisely because of how improbable they seem. Fish, after all, are often associated with movement, speed, and active hunting. In the trench, snailfish appear gelatinous, slow-moving, and almost shapeless. Their bones are reduced. Their muscles are soft. Their bodies are adapted to match the density of the surrounding water, minimizing energy expenditure. For years, scientists debated whether vertebrates could exist at the deepest depths at all. The discovery of snailfish living near the bottom of the trench forced a re-evaluation. These animals are not simply tolerating pressure, they require it. When brought toward the surface, their tissues fail. The environment that kills humans is the one that keeps them intact. This inversion is deeply unsettling. It suggests that habitability is not a universal scale, but a context-dependent one. Conditions that appear hostile from one perspective may be optimal from another. The trench becomes a mirror, reflecting the narrowness of human assumptions. Other trench inhabitants push this idea even further. Some organisms lack eyes entirely. Others possess sensory structures so sensitive they can detect minute vibrations caused by distant movement. Many have slow metabolisms, conserving energy to an extreme degree. Growth rates are measured in years rather than weeks. Reproduction is infrequent but efficient. There are also creatures whose life cycles remain only partially understood. Larval stages may drift at higher depths before settling into the trench. Adults may move vertically over distances that challenge tracking. Because direct observation is limited, much of what scientists infer comes from indirect evidence and fragmented data. This uncertainty adds to the unease. When researchers cannot observe a full life cycle, they must accept gaps in understanding. In most environments, those gaps can be filled with repeated visits and long-term monitoring. In the trench, access is so limited that each observation feels precious, and each unanswered question lingers longer than usual. One of the most disturbing discoveries has been the presence of life forms that incorporate human-made pollutants into their tissues. Chemical analyses of trench organisms have revealed compounds associated with industrial processes, plastics, and persistent organic pollutants. These chemicals should not be here, and yet they are. This means that even creatures that evolved in permanent darkness under crushing pressure are not isolated from surface activity. The trench is not sealed off. It is connected through slow but relentless pathways of sinking particles and circulating currents. The idea that nothing from the surface reaches the deepest parts of the ocean is no longer defensible. For scientists, this realization complicates the narrative of resilience. These organisms are adapted to extremes, but not necessarily to contamination. Their slow metabolisms and long lifespans may make them particularly vulnerable to pollutants that accumulate over time. The very traits that allow survival in scarcity could become liabilities in a changing chemical environment. There are also life forms in the trench that appear almost static. Sponges, worms, and microbial mats anchor themselves to the seafloor, relying on slow flows of nutrients. Their existence challenges assumptions about activity and movement as markers of life. Here, persistence matters more than speed. Microbial life deserves particular attention. Bacteria and archaea dominate much of the trench ecosystem, driving chemical cycles that sustain larger organisms. These microbes operate under pressures and temperatures that alter fundamental biochemical processes. Some use metabolic pathways rarely seen at the surface. Others appear to repair damage from pressure-induced stress continuously. Understanding these microbes is not just an academic exercise. Their metabolic strategies may inform biotechnology, medicine, and our understanding of early life on Earth. Yet studying them in situ is extraordinarily difficult. Sampling often alters the very conditions scientists wish to observe. The presence of these creatures forces scientists to confront uncomfortable questions about the limits of prediction. If life can adapt so completely to permanent darkness and crushing pressure, what other environments might be viable? How many assumptions about habitability are based more on familiarity than on necessity? This question extends beyond biology. It touches on philosophy and methodology. Scientists rely on models built from known systems. The trench repeatedly produces exceptions that require those models to be adjusted. This is not failure. It is how science progresses. But it is also unsettling, because it reveals how provisional understanding always is. There is also a psychological dimension to encountering life in the trench. Humans tend to associate danger with visible threats. Teeth, claws, movement. Trench creatures are rarely threatening in that sense. They do not chase. They do not attack. Their existence is unsettling precisely because it is quiet and indifferent. They do not acknowledge human presence. When illuminated, they may drift away or continue their behavior unchanged. There is no sense of interaction, no mutual awareness. This indifference reinforces the feeling that humans are intruders, not participants. Some scientists describe a sense of unease that lingers after studying trench life. Not fear of being harmed, but discomfort at witnessing a world that operates entirely outside human norms. These organisms do not need light. They do not need speed. They do not need abundance. They have found equilibrium in conditions that humans experience only as threat. The phrase, "shouldn't exist," ultimately says more about human expectations than about reality. The trench exposes how narrow those expectations can be. It reminds scientists that evolution does not optimize for comfort or familiarity. It optimizes for survival under whatever conditions persist long enough. This realization does not make the trench less frightening. It makes it more complex. Fear rooted in ignorance can be resolved with knowledge. Fear rooted in humility tends to persist. The more scientists learn about trench life, the more they recognize how little of Earth's biological potential has been explored. As exploration continues, each new creature documented adds another piece to a puzzle that resists completion. These organisms are not anomalies to be dismissed. They are evidence that life's adaptability extends further than once believed. And as attention gradually shifts from individual species to entire ecosystems, a broader picture begins to form. The trench is not a chaotic assemblage of survivors. It is a functioning system, balanced on slow inputs and long timescales, shaped by forces that operate beyond human experience. Understanding how such a system maintains stability requires more than cataloguing its inhabitants. It demands attention to interactions, energy flows, and feedback loops that are still poorly understood. And as scientists begin to listen more closely, another unsettling realization emerges. The trench is not silent. It is not static. Beneath the pressure and darkness, it produces sounds, movements, and signals that challenge assumptions about what a place without light should feel like. And it is there, in those subtle disturbances, that the next layer of unease begins to take shape. When people imagine the deepest parts of the ocean, silence is usually the first thing that comes to mind. Complete darkness paired with complete quiet. A place so far removed from surface life that nothing disturbs it. For scientists who work with deep-sea acoustics, this assumption fades quickly. The deeper they listen, the more they realize that the ocean, even at its greatest depths, is never truly silent. In the Mariana Trench, sound behaves differently than it does in air. Water is an efficient carrier of vibration. Sound waves travel farther, faster, and with less loss of energy. At depth, where light disappears and vision becomes unreliable, sound becomes the dominant source of information. This is as true for marine life as it is for scientists attempting to understand what happens far below the surface. The first time researchers lowered sensitive hydrophones into the deep ocean, they expected long stretches of near silence punctuated by the occasional noise. What they found instead was a constant background presence, a low, uneven hum, pulses, rhythms, irregular bursts of sound that could not be easily traced to a single source. The trench, it turned out, was listening back. Some of these sounds originate from geological processes. The Earth is not still beneath the ocean. Tectonic plates grind against one another. Sediments shift. Subtle fractures propagate through rock under immense stress. These movements generate low-frequency vibrations that travel through water and solid material alike. In shallower regions, such signals are often drowned out by surface noise. In the depths of the trench, they can be detected with startling clarity. Seismic activity does not always announce itself as an earthquake. Many events are too small to be felt at the surface, yet they still release energy. Hydrophones placed near the trench floor have recorded these faint signatures, revealing a slow conversation between the ocean and the planet's interior. For scientists, this offers valuable data. It also reinforces the sense that the trench is not a passive void, but an active interface. Other sounds come from the water itself. Currents move differently at depth, guided by temperature gradients and the shape of the sea floor. When these flows interact with steep trench walls, they generate turbulence. This turbulence produces noise that can persist for hours or days, shifting subtly as conditions change. Unlike surface waves, these movements are invisible. Only sound reveals their presence. Then there are biological sounds. Even in permanent darkness, life communicates, navigates, and interacts acoustically. Some trench organisms produce sounds deliberately, though often at frequencies outside the range of human hearing. Others generate noise incidentally through movement, feeding, or contact with the seafloor. The cumulative effect is a soundscape that feels alive, if unfamiliar. One of the most unsettling aspects for researchers is the unpredictability. Sounds appear without warning. Patterns emerge and dissolve. A hydrophone might record hours of low-level noise, followed by a sudden sharp signal that defies easy explanation. Sometimes these sounds are traced back to distant storms at the surface, their energy transmitted through the ocean over vast distances. Other times the source remains uncertain. Surface activity influences the trench more than the intuition suggests. Storms thousands of kilometers away can generate waves that couple with deep water layers, sending pressure fluctuations downward. These signals arrive long after the storm itself has passed, echoing through the depths like delayed whispers. The trench records these events quietly, continuously. Human activity adds another layer. Ships, even far from the trench, produce low-frequency noise that travels efficiently through water. Industrial activity, sonar use, and seismic surveys contribute to a growing background hum. Hydrophone recordings from the deepest parts of the ocean have captured these sounds, distorted but recognizable. This means that even at extreme depth, the presence of human civilization is audible. For scientists, this realization is unsettling. The trench feels remote, yet it is not acoustically isolated. Sound connects distant places in ways light and physical contact do not. A noise generated at the surface can reach the deepest parts of the ocean long after its source has vanished. The trench becomes a kind of archive, storing echoes of events that happened far away. Listening at depth also changes how scientists think about danger. In darkness, sound can signal movement before it becomes visible. Submersible operators learn to pay attention to acoustic feedback. Unusual vibrations can indicate structural stress, contact with the seafloor, or changes in surrounding conditions. Sound becomes a diagnostic tool, one that can offer warning where vision cannot. There is also the psychological effect of constant sound. Silence, when it occurs, is often interpreted as safety. Noise suggests activity, unpredictability, change. In the trench, there is always something happening, even if it is subtle. For crewed missions, this awareness can be disconcerting. The environment never feels entirely still. Some sounds recorded in the deep ocean have resisted clear classification. Researchers label them descriptively rather than definitively, based on their acoustic signatures. Long moaning tones, sharp clicks, rhythmic pulses. Over time, some of these sounds have been linked to known sources, such as ice movement or distant seismic events. Others remain ambiguous. Ambiguity is not inherently threatening, but in an environment already defined by limited visibility and extreme conditions, it adds to unease. When scientists cannot immediately explain a signal, they must consider a wide range of possibilities: equipment malfunction, environmental noise, biological activity, geological processes. Each explanation carries different implications. The trench's soundscape also reveals how life adapts to darkness. Some organisms rely heavily on mechanoreception, sensing vibrations rather than light. For them, sound is not noise, it is information. A disturbance in the water may signal food, danger, or opportunity. The trench is quiet by human standards, but for its inhabitants it is rich with cues. Researchers studying these organisms must be careful not to overwhelm them. Artificial noise from submersibles can disrupt behaviour. Lights attract or repel, sound travels far, and a single expedition can alter local conditions temporarily. This awareness has led to more cautious approaches, with quieter propulsion systems and passive listening prioritised over active probing. The idea that the trench never truly goes silent challenges a common metaphor. Darkness is often equated with emptiness, stillness, absence. Sound reveals the opposite. Even in permanent midnight, processes unfold continuously. Energy moves, matter shifts, life responds. For scientists, listening becomes a way to extend perception beyond visual limits. Acoustic data fills gaps that cameras cannot. It provides temporal continuity, recording changes over days or months rather than moments. Hydrophones left in place can capture patterns invisible to short-term observation. These long-term recordings sometimes reveal cycles, slow oscillations in background noise tied to oceanographic processes, seasonal variations transmitted from the surface, even subtle changes in tectonic stress. The trench, it seems, has rhythms of its own, even without sunlight to mark time. Understanding these rhythms is still an ongoing effort. Data sets are incomplete. Instruments are expensive and vulnerable. Retrieval is uncertain. Each recovered recording offers a glimpse into a world that operates largely beyond human senses. The presence of sound also complicates the idea of isolation. The trench is deep, but it is not cut off. It is connected through water, through vibrations, through energy pathways that ignore human boundaries. This connectivity is both scientifically valuable and emotionally unsettling. When scientists speak about fear in relation to the trench, it is often this combination that surfaces: darkness without silence, depth without stillness, an environment that cannot be fully seen, yet is constantly active. The mind expects emptiness and encounters motion instead. As research continues, sound remains one of the most powerful tools for understanding the trench. It reveals processes that light cannot. It uncovers connections that distance hides. And it reminds scientists that even in the deepest parts of the ocean, the planet is always doing something. From here, attention begins to shift again. Beyond sound and movement, the trench hides another layer of complexity. Temperature, chemistry, and pressure interact in ways that challenge existing models. The environment is not just dark and loud in its own subtle way. It is chemically strange, thermally stable yet fragile, and capable of altering matter over time. And as scientists begin to examine those invisible forces more closely, the sense of unease deepens further. Cold in the deep ocean is not the sharp, biting cold of winter air or icy wind. It is something slower, heavier, and far more patient. It settles into everything. It does not shock the body so much as it drains it, molecule by molecule, until motion itself feels expensive. When scientists talk about the deepest parts of the ocean, temperature is often mentioned almost casually. Just a few degrees above freezing. Stable. Predictable. And yet, in the environment of the Mariana Trench, cold is not merely a background condition. It is a governing force, intertwined with darkness and pressure in ways that quietly reshape chemistry itself. At the surface, temperature fluctuates constantly. Day and night cycles, seasons, weather patterns, and currents all conspire to create variation. Life adapts to these changes with flexibility. Metabolisms speed up and slow down. Behaviours shift. Ecosystems pulse. None of that applies in the trench. Here, temperature barely changes over the course of a year or even a century. The cold is steady, unwavering, and deeply embedded in every process that occurs. For scientists, this stability initially seems reassuring. Stable systems are easier to model. Variables can be controlled. But as research progressed, it became clear that this cold stability produces outcomes that are anything but simple. Chemical reactions slow dramatically at low temperatures. Diffusion rates change. Solubility behaves differently. Combine this with crushing pressure and total darkness, and familiar rules begin to bend. One of the first surprises came from measurements of dissolved gases. Oxygen, carbon dioxide, methane, and other compounds behave differently under extreme pressure. Gases dissolve more readily, concentrations shift, chemical equilibria that hold at the surface no longer apply. This means that the water itself becomes chemically distinct, not just biologically unusual. In the trench, oxygen is present, but its availability varies with depth and circulation. Deep waters are often well oxygenated because cold water can hold more dissolved oxygen. This supports life in ways that once seemed impossible at such depths. At the same time, low temperatures slow metabolic processes, creating a strange balance between supply and demand. Carbon chemistry becomes particularly complex. Organic matter sinking from the surface undergoes gradual transformation as it descends. By the time it reaches trench depths, it has been altered by microbes, pressure, and time. What arrives is not fresh material, but a chemically aged version, stripped of easy energy. Life that feeds on it must be adapted to extract value from what remains. Then there is methane. In some deep sea environments, methane seeps from the seafloor, fueling chemosynthetic communities. In the trench, methane chemistry is influenced by pressure and temperature in ways that scientists are still trying to untangle. Methane can become trapped in crystalline structures known as hydrates, stable only under specific conditions. These hydrates lock away carbon in solid form, altering how energy flows through the system. Pressure and cold also affect how metals and minerals dissolve and precipitate. Elements such as iron, manganese, and sulfur cycle through different chemical states depending on local conditions. These cycles influence microbial metabolism and, by extension, the entire ecosystem. Small changes in chemistry can cascade outward, affecting which organisms can survive and how they interact. What makes this particularly unsettling is how difficult it is to observe these processes directly. Sampling water at trench depths risks altering its chemistry before it can be analysed. Pressure changes during retrieval cause gases to come out of solution. Temperatures rise, reactions accelerate. By the time a sample reaches the surface, it may no longer reflect in situ conditions. Scientists attempt to compensate with specialised equipment designed to seal samples at depth, preserving pressure and temperature. Even then, limitations remain. Instruments can fail, seals can leak. The act of observation itself introduces uncertainty. This means that much of what is known about trench chemistry is inferred rather than directly measured. Darkness compounds the problem. Without sunlight, photochemical reactions cease. At the surface, light drives many chemical transformations, breaking down compounds and initiating reactions. In the trench, chemistry proceeds without this input. Instead, it relies on thermal energy, pressure, and biological activity. This creates pathways that are slower, more subtle, and harder to detect. For scientists trained in surface chemistry, this environment feels unfamiliar. Reaction rates must be recalculated. Assumptions about equilibrium must be questioned. Even basic parameters like pH behave differently under extreme pressure. The trench is not just cold and dark, it is chemically other. One of the most troubling discoveries has been the presence of synthetic chemicals in trench waters and sediments. Compounds associated with industrial activity have been detected at depths once thought unreachable by pollution. These chemicals interact with the cold, high-pressure environment in unpredictable ways. Some persist longer than expected, others break down into unknown byproducts. The cold slows degradation. Pressure alters molecular structure. Darkness removes photodegradation pathways. Together, these factors create a setting where contaminants can linger, accumulating in organisms that have no evolutionary history with such substances. For scientists, this raises ethical and practical concerns. The trench is resilient, but not invulnerable. Temperature also affects physical properties of water itself. Density gradients at depth influence circulation patterns. Cold, dense water can remain isolated for long periods, trapping chemical signatures. When mixing does occur, it can redistribute substances across large vertical distances. Understanding these movements is essential for interpreting chemical data, yet they are difficult to observe directly. The interaction between cold and pressure extends into geology as well. Chemical reactions between seawater and the seafloor contribute to mineral formation and alteration. Over time, these processes influence the composition of sediments and the stability of slopes. In a trench, where gradients are steep, small changes can have significant consequences. For scientists, the unknown chemistry of the deep introduces a kind of cognitive unease. In many fields, uncertainty decreases as instruments improve. In the trench, improved instruments often reveal additional complexity rather than clarity. Each new measurement raises further questions. Why does this compound behave differently here? What pathway produced that signal? What process is missing from the model? This uncertainty is not failure, it is information. It signals that the environment operates under constraints rarely encountered elsewhere. But it does challenge the comforting idea that deeper understanding always leads to simplification. Sometimes it leads to richer, messier pictures. Cold also influences biological chemistry in profound ways. Enzymes in trench organisms are adapted to function at low temperatures and high pressures simultaneously. These enzymes are often unstable at surface conditions, making them difficult to study. Yet they hold clues to how life can operate under extremes. The structural chemistry of proteins in these organisms reveals subtle adaptations. Amino acid sequences favour flexibility. Molecular bonds are arranged to resist pressure-induced distortion. These features are invisible without detailed analysis, yet they determine survival. For scientists, studying these adaptations requires interdisciplinary collaboration. Biology, chemistry, physics, and geology intersect in the trench. No single discipline provides a complete picture. This necessity for integration can be intellectually rewarding, but it also underscores how complex the environment truly is. The cold, dark chemistry of the trench also challenges assumptions about time. Reaction rates are slow. Changes accumulate over decades or centuries. Experiments designed around short timescales may miss critical dynamics. Long-term monitoring is ideal, but difficult to sustain in such an extreme setting. This temporal mismatch contributes to a lingering sense of incompleteness. Scientists know that what they observe during a brief expedition represents only a snapshot. The system continues to evolve quietly, long after instruments are retrieved. Processes unfold without witnesses. There is also the question of thresholds. Cold and pressure create conditions where small perturbations may trigger disproportionate responses. A slight change in temperature or chemistry could alter microbial communities, which in turn could affect larger organisms. Predicting these responses is challenging when baseline conditions are still being mapped. As climate change alters surface oceans, scientists are increasingly concerned about how those changes propagate downward. Warming waters, altered circulation, and shifting chemistry may eventually reach even the deepest parts of the ocean. The trench, once thought stable on human timescales, may not be immune. This possibility adds urgency to research, but also caution. The unknown chemistry of the deep is not just an academic curiosity. It has implications for global cycles, ecosystem resilience, and our understanding of Earth as an interconnected system. Cold, darkness, and pressure together create an environment that resists simplification. They slow processes, hide signals, and challenge assumptions. For scientists, working in this space requires patience and humility. It means accepting that some answers will come slowly, and some may remain provisional for a long time. The trench does not reveal itself easily. Its chemistry unfolds quietly, governed by forces that operate beyond everyday experience. Each new measurement is a reminder that the deepest parts of the ocean are not just colder and darker versions of the surface world. They are chemically distinct realms with their own rules. As attention shifts from chemistry toward human interaction with this environment, another set of concerns begins to emerge. The trench is difficult to reach, difficult to study, and difficult to leave unchanged. Technology, for all its sophistication, has limits here, and when those limits are tested, the consequences can be immediate and severe. Every successful deep-sea mission creates the illusion of control. Instruments function, data returns, video footage is reviewed calmly in laboratories far from the ocean. From the outside, it can appear as though the deepest parts of the planet have been rendered manageable by engineering and planning. Scientists know better. They understand that each descent into extreme depth is less a demonstration of mastery and more a narrow negotiation with failure. Nowhere is this more evident than in missions aimed at the Mariana Trench, where the margin between success and disaster is measured not in meters, but in millimeters and milliseconds. At those depths, technology does not fail gradually. It either works or it collapses. The history of trench exploration is filled with missions that came back altered, damaged, or nearly lost altogether. These stories are rarely told dramatically by the scientist involved. They are recounted quietly, with careful wording and an emphasis on lessons learned. But beneath that professional restraint lies a shared understanding. Every mission that returns is also a reminder of how easily it might not have. Pressure is the most obvious threat, but it is far from the only one. Electronics behave unpredictably under compression. Insulation materials that function flawlessly at the surface can crack or deform at depth. Wiring becomes brittle, solder joints fail, tiny imperfections, invisible during inspection, can propagate rapidly once exposed to thousands of atmospheres. One recurring issue in deep-sea missions is seal failure. Submersibles and remotely operated vehicles rely on complex networks of seals to keep water out of sensitive components. These seals are tested extensively, yet the combination of pressure, cold, and time can cause subtle changes in material properties. A seal that held during descent may begin to leak after hours at depth. Water intrusion does not announce itself loudly. It creeps in, damaging electronics silently until systems begin to behave erratically. Communication failures are another persistent risk. Radio waves do not travel well through water, especially at depth. Most communication relies on acoustic signals, which are slower and more limited. Commands sent from the surface may take time to reach a vehicle. Data returns may be delayed or incomplete. If communication is lost entirely, operators must decide whether to wait, attempt recovery, or accept loss. There have been missions where remotely operated vehicles descended smoothly, completed their objectives, and then failed during ascent. Buoyancy systems designed to counteract immense pressure can malfunction. A stuck valve or jammed release mechanism can trap a vehicle at depth. Recovery attempts may be impossible if the system cannot respond. Crews are trained to anticipate these scenarios, but preparation does not eliminate anxiety. When a vehicle stops responding, minutes stretch into hours. Engineers review telemetry logs repeatedly, searching for clues. Calculations are rechecked. The ocean above remains calm, offering no hint of the drama unfolding kilometers below. Crewed missions amplify these stakes. When humans are inside a pressure vessel, every system failure carries immediate personal risk. Life support must function continuously. Carbon dioxide scrubbing systems must remain efficient. Power supplies must not falter. Even small deviations can become critical over long descents and ascents. One of the most sobering aspects of these missions is how quickly situations can deteriorate. A minor leak detected at the surface might be manageable. At depth, the same leak can become catastrophic. Pressure does not allow for improvisation. There is no equivalent of stepping outside to make a repair. Everything must be resolved from within a sealed environment. There have been instances where crews heard unexpected sounds during descent, sharp bangs, persistent creaks, low-frequency vibrations that did not match predictions. Each sound triggered immediate analysis. Was it thermal contraction, pressure equalization, structural stress, or something worse? Often, answers came only after the mission ended, when the vehicle was inspected and damage assessed. For scientists and engineers, these moments leave lasting impressions. Even when no injury occurs, the awareness of vulnerability lingers. The trench does not provide feedback in familiar ways. Problems must be inferred from indirect signals. Decisions must be made with incomplete information. Uncrewed missions are not immune to these challenges. Autonomous vehicles operate without real-time human intervention. They follow pre-programmed instructions, adjusting behavior based on sensor input. When something unexpected happens, their responses are limited by code written months or years earlier. A scenario not anticipated during design may lead to failure. Losses are part of the history of trench exploration. Instruments have been crushed beyond recovery. Vehicles have vanished, leaving behind only incomplete data and unanswered questions. Each loss represents not just financial cost, but the disappearance of unique information gathered under conditions unlikely to be replicated soon. These incidents contribute to a culture of caution. Scientists planning new missions often study past failures as closely as past successes. Design reviews focus on redundancy. Single points of failure are scrutinized, materials are selected conservatively. Even then, uncertainty remains. The ocean introduces variables that resist full control. Currents can shift unexpectedly. Sediment can obscure sensors or clog mechanisms. Biological growth can interfere with moving parts. Chemical interactions between seawater and materials can weaken components over time. Recovery itself is a delicate phase. Ascending from extreme depth places different stresses on systems than descent. Pressure decreases gradually, but materials respond unevenly. Components that adapted to compression may behave unpredictably as that compression is released. Timing matters, speed matters, coordination matters. For scientists involved in these missions, relief often comes only after a vehicle is safely back on deck. Even then, inspections may reveal damage that went unnoticed during operation. Deformed structures, cracked housings, systems that function just long enough to complete the mission. These discoveries reinforce a central truth. Technology extends human reach, but it does not eliminate risk. In environments like the trench, technology operates at the edge of its capabilities. Each success is provisional, contingent on countless factors aligning correctly. This reality shapes how scientists talk about fear. It is not fear of the unknown in a mythical sense. It is fear grounded in experience, in knowledge of how systems fail and how unforgiving the environment can be. It is the awareness that confidence must always be tempered by respect. The trench does not reward bravado. It exposes overconfidence quickly. Engineers and researchers who have spent years working in this field often develop a quiet humility. They trust their designs, but never completely. They celebrate successes, but never assume they will be repeated easily. As missions become more ambitious, reaching deeper and staying longer, the complexity increases. More systems mean more potential failure points. More data means more reliance on uninterrupted operation. The balance between scientific reward and operational risk becomes increasingly delicate. Despite this, exploration continues, not because scientists underestimate the dangers, but because the knowledge gained is considered worth the effort. Each mission refines understanding, improves technology, and informs future designs. Failures, when they occur, become part of that process. The stories of missions that almost did not come back rarely end with triumph. They end with reflection. What went wrong? What nearly went wrong? What could be done differently next time? These reflections are not signs of weakness. They are signs of a field that understands its limits. As attention shifts from the fragility of technology to the broader implications of exploration, another question begins to surface. Given the risks, the costs, and the limitations, why is so much of the trench still unexplored? Why, after decades of effort, does the deepest part of our planet remain largely unmapped and poorly understood? The answer lies not only in danger, but in scale, accessibility, and the sheer difficulty of sustained presence in a place that resists it at every level. By now, it might seem reasonable to assume that the deepest place on Earth would be one of the most carefully studied. After all, humans have walked on the moon, mapped distant planets, and sent probes beyond the edges of the solar system. From that perspective, the idea that a place on our own planet remains largely unexplored feels almost embarrassing. And yet, the Mariana Trench remains one of the least understood environments on Earth, not because of a lack of interest, but because of a convergence of obstacles that quietly resist resolution. The first and most obvious reason is scale. The trench is not a single point that can be visited, photographed, and checked off a list. It is a long, narrow system stretching for thousands of kilometers, with steep walls, variable depths, and complex internal structure. Even defining what counts as explored becomes difficult. A single descent to the deepest point does not meaningfully characterize the entire trench, any more than visiting the lowest point in a canyon explains the whole landscape. Mapping the trench in detail requires repeated passes with specialized instruments, operating close to the seafloor under extreme conditions. Each pass covers only a small area. High-resolution mapping takes time, and time at depth is expensive. Ships capable of supporting such missions are limited in number. Crews are specialized. Weather windows are narrow. Logistics dominate every decision. Cost alone is enough to slow exploration dramatically. A single deep-sea expedition can cost millions of dollars. Designing, building, and maintaining pressure-resistant vehicles adds further expense. Unlike space missions, which often capture public imagination and political support, deep-sea exploration operates largely out of view. Funding competes with more immediately visible scientific priorities. There is also the issue of accessibility. The trench lies far from major ports, in open ocean regions that require long transit times. Reaching the site can take weeks. During that time, ships consume fuel, crews rotate shifts, and schedules tighten. Any delay, whether from weather or mechanical issues, ripples through the mission plan. Even once on site, operations are constrained. Launching and recovering vehicles in open ocean conditions is delicate. Rough seas can halt work entirely. Equipment must be handled carefully to avoid damage before it ever reaches the water. These practical considerations limit how often and how deeply missions can probe. Technology, as powerful as it is, introduces its own bottlenecks. Submersibles and remotely operated vehicles require constant maintenance. Pressure testing is rigorous and time-consuming. Components that have been stressed at depth may need replacement even if no failure occurred. Turnaround between missions can take months or years. Autonomous systems offer some advantages, but they come with trade-offs. Autonomous vehicles must be programmed in advance, limiting flexibility. They cannot adapt easily to unexpected discoveries. Data retrieval may occur long after deployment, delaying analysis and feedback. If something goes wrong, intervention is often impossible. Communication constraints further complicate exploration. Real-time control is limited by the physics of sound transmission through water. Operators must anticipate scenarios rather than respond instantly. This reduces the ability to conduct exploratory work that depends on improvisation and curiosity-driven decision-making. There is also the matter of scientific prioritization. The ocean is vast and resources are finite. Scientists must decide where to focus effort. Coastal ecosystems, fisheries, climate-related processes, and shallow marine environments often receive priority because their impacts are immediate and measurable. The trench, by contrast, feels distant from daily human concerns, even though it plays a role in global systems. Another factor is data density. Exploring the trench yields small amounts of data relative to the effort invested. A single mission may return hours of footage and a handful of samples. Interpreting these requires years of analysis. In fields where large data sets drive progress, this slow accumulation can be frustrating. Risk tolerance also plays a role. Every mission carries the possibility of equipment loss or failure. Institutions must weigh the potential scientific return against the chance of losing expensive assets. This calculation tends to favour caution. Incremental advances are preferred over bold, risky exploration. There is also an ethical dimension that has become more prominent in recent years. As scientists learn more about trench ecosystems, concerns arise about disturbance. Introducing vehicles, lights, noise, and sampling tools alters the environment, even if temporarily. In an ecosystem adapted to stability and scarcity, disruption may have lasting effects. This awareness leads to restraint. Just because a place can be visited does not mean it should be visited frequently. Some researchers argue for minimal intervention, prioritizing passive observation over active exploration. This philosophy, while respectful, further limits data collection. The trench also challenges traditional scientific workflows. Experiments are difficult to repeat. Conditions cannot be easily replicated. Controls are hard to establish. This makes hypothesis testing slower and more uncertain. Findings often rely on convergence of evidence rather than direct proof. There is a cultural component as well. Scientific communities develop around shared methods and accessible environments. Fewer researchers specialize in Hadal science because opportunities are limited. Training pathways are narrow. Expertise accumulates slowly. This creates a bottleneck in human capital as much as in technology. Public perception influences exploration indirectly. Space exploration benefits from a narrative of outward expansion and discovery. The deep ocean lacks a comparable cultural framework. It is perceived as dark, dangerous, and abstract. Without sustained public interest, funding and attention fluctuate. Even language reflects this distance. We talk about going to space as an adventure. We talk about descending into the trench with caution. The metaphors themselves shape expectations and priorities. Despite these challenges, exploration does occur. Each mission expands the map slightly. Each data set fills in gaps. Progress is real, but it is slow by necessity. The trench resists rapid understanding not because it is deliberately hidden, but because it exists under conditions that limit human presence. The irony is that in some ways, the trench is more accessible than distant planets. It is physically closer. Yet proximity does not equal ease. The environment imposes constraints that rival or exceed those of space, often without the same technological spin-offs or public enthusiasm. Scientists who work in this field tend to emphasize patience. They frame exploration as a long-term endeavor measured in decades rather than danger itself drives persistent unease. The trench embodies uncertainty. It is difficult to access, difficult to monitor, and slow to reveal patterns. Answers arrive incrementally, often raising new questions rather than resolving old ones. This ongoing uncertainty can be mentally taxing. Scientists accustomed to iterative progress may find the pace frustrating. The sense that complete understanding may never be achieved adds a subtle pressure. It is not despair, but a recognition of limits. Endless depth also alters the perception of time. Processes in the trench unfold slowly. Sedimentation occurs over centuries. Biological growth spans decades. Geological changes stretch across millennia. Human timescales feel irrelevant. This mismatch can produce a feeling of disconnection, as if observing a world that operates independently of human concerns. For some researchers, this is precisely what draws them to the trench. The psychological challenge becomes part of the appeal. Confronting environments that resist comprehension can be intellectually invigorating. Yet even those who are drawn to it acknowledge the unease. The fear of endless depth is not something to be overcome entirely. It serves a function. It encourages caution. It tempers ambition. It reminds scientists to respect environments that cannot be rushed or dominated. In this sense, fear becomes a tool rather than an obstacle. As research progresses, scientists learn to coexist with this discomfort. They design missions that acknowledge psychological as well as technical limits. Crew rotations, communication protocols, and mission durations are planned with mental well-being in mind. Even uncrewed operations are structured to reduce cognitive strain on operators. The trench thus shapes not only scientific questions, but scientific behavior. It influences how teams work, how risks are assessed, and how success is defined. Understanding does not eliminate fear, it reframes it. And as attention shifts from the internal experience of fear to the broader implications of depth, another realization emerges. Endless depth is not just a psychological challenge. It has practical consequences for how Earth functions as a system. The trench is not merely something to be feared or admired. It plays a role in shaping the planet itself, influencing processes that extend far beyond its dark, distant walls. For a long time, the deepest parts of the ocean were treated as geological afterthoughts. They were places where the seafloor happened to dip lower than elsewhere, interesting mainly for record-setting depths and extreme conditions. That view has changed steadily as scientists began to understand that the trench is not an isolated feature, but a visible expression of systems that operate far beyond human senses. The Mariana Trench is not just a hole in the seafloor. It is a window into processes that shape the planet from the inside out. One of the most important realizations to come from trench research is that Earth's surface and interior are not separate realms. They are connected through slow, powerful mechanisms that operate continuously, regardless of whether humans are watching. The trench marks a boundary where one tectonic plate slides beneath another, a process known as subduction. This movement is not dramatic on human timescales. It proceeds at roughly the speed fingernails grow, yet over millions of years it reshapes continents, drives earthquakes, and recycles vast amounts of material back into the mantle. What makes the trench unsettling to scientists is not just that this process exists, but that it is ongoing. The seafloor beneath the trench is being pulled downward right now. Sediments, water, and even traces of biological material are being carried into the Earth's interior. This is not a static scar left behind by ancient forces. It is an active interface between the surface world and the deep Earth. Studying this interface has revealed that oceans play a far more active role in Earth's internal dynamics than once believed. Water does not simply sit on top of the crust, it infiltrates it. As tectonic plates bend and fracture near trenches, seawater seeps into cracks and reacts chemically with rock. These reactions alter the physical properties of the crust, changing how it behaves under stress. When this altered crust is dragged downward, the water it contains is released at depth. That release influences the behavior of the mantle, lowering melting points and contributing to volcanic activity elsewhere. In this way, the trench becomes part of a global cycle that links oceans, earthquakes, volcanoes, and the formation of new crust. For scientists, this interconnectedness is both fascinating and unsettling. It means that events occurring far below the ocean's surface can influence landscapes thousands of kilometers away. An earthquake generated along a subduction zone can send shockwaves through the planet. Volcanic arcs form as a consequence of processes initiated deep beneath the trench. The surface world responds to actions that are invisible and slow. The trench also reveals how Earth regulates itself over geological time. Carbon, for example, is not confined to the atmosphere and biosphere. It cycles through the planet's interior. Organic carbon trapped in sediments is carried into subduction zones, where some of it is released back to the surface through volcanic gases, while some is locked away for millions of years. This long-term carbon cycle helps stabilize Earth's climate over deep time. Understanding this cycle requires data from places like the trench. Chemical analyses of sediments and fluids provide clues about what is being transported downward and what is released upward. These measurements are difficult to obtain, but they are essential for building accurate models of Earth's behavior. The trench also plays a role in ocean circulation. Cold, dense water sinks in polar regions and flows along the seafloor, eventually reaching deep trenches. These deep currents move slowly, but they transport heat, nutrients, and dissolved gases across vast distances. The trench acts as a pathway and a reservoir, influencing how these deep waters mix and circulate. This circulation affects the distribution of oxygen and nutrients throughout the deep ocean. It shapes ecosystems far from the trench itself. Changes in circulation patterns can alter conditions over large regions, linking deep sea processes to surface productivity and climate. What unsettles scientists is how sensitive these systems can be. Small changes in temperature, chemistry, or circulation at the surface can propagate downward over time. Conversely, changes in deep processes can influence the surface in delayed and indirect ways. Cause and effect are separated by distance and time, making relationships difficult to trace. The trench also offers insight into how Earth dissipates energy. Tectonic stress builds slowly as plates move, then releases suddenly during earthquakes. The geometry of subduction zones influences how and where this energy is released. Studying the trench helps scientists understand why some regions experience frequent small earthquakes, while others accumulate stress for long periods before releasing it catastrophically. These insights are not purely academic, they inform hazard assessments for coastal regions around the Pacific. Understanding subduction dynamics helps improve models of earthquake and tsunami risk. The trench, remote as it is, has implications for millions of people living far away. There is also the question of how life interacts with these hidden systems. Microbial communities in trench sediments may influence chemical reactions that occur as material is subducted. Life is not merely a passenger in these processes. It can alter the chemistry of sediments, affecting what enters the mantle and how it behaves. This challenges the traditional separation between geology and biology. In the trench, the two are intertwined. Biological activity modifies geological material, which in turn influences geological processes. This feedback loop operates slowly but persistently. For scientists, this blurring of boundaries complicates understanding. It requires integrating data across disciplines that historically developed separately. Geophysics, geochemistry, oceanography, and biology must all contribute to a coherent picture. No single field can fully explain what the trench reveals. The trench also forces reconsideration of the Earth's apparent stability. From a human perspective, the planet feels solid and predictable. Continents seem fixed, Oceans seem constant. The trench undermines that illusion. It is a reminder that Earth is dynamic at every scale, even when change is imperceptible day to day. This dynamism can be unsettling because it highlights how little control humans have over fundamental planetary processes. We can measure, model, and predict to some extent, but we cannot stop plates from moving or pressure from building. The trench is a place where that lack of control is impossible to ignore. At the same time, the trench provides reassurance of a different kind. It shows that Earth has mechanisms for recycling material and energy over immense timescales. The planet is not static, but it is not chaotic either. Patterns exist, even if they unfold slowly and invisibly. For scientists, working with these patterns requires patience and humility. Data from the trench rarely produce immediate answers. Instead, they add constraints, refine models, and sometimes challenge long-held assumptions. Progress is incremental. This incremental nature can feel frustrating, especially when compared to fields where experiments can be repeated easily and results obtained quickly. In trench research, each data point is hard-won. Each measurement carries weight. The emotional response to this reality varies. Some scientists find it grounding, others find it unsettling. Knowing that vast systems operate beneath our feet and beneath the oceans can provoke a sense of insignificance. It can also inspire awe at the complexity of the planet. As research continues, the trench increasingly appears not as an extreme outlier, but as a key component of Earth's functioning. It connects surface processes to the deep interior. It influences cycles that shape climate, geology, and life. This realization reframes the question of why the trench matters. It is not important because it is deep. It is important because it reveals how interconnected the planet truly is. The deepest place on Earth is not isolated. It is woven into systems that touch every part of the globe. And as scientists absorb this perspective, another question arises. If the trench plays such a fundamental role in Earth's systems, what else might it be hiding? Beyond known processes and measured cycles, could there be phenomena not yet recognized, operating under conditions so extreme that they challenge existing frameworks entirely? When scientists say that the deep ocean is poorly understood, they are not being modest. They are stating a practical limitation. Large portions of the deeper seafloor have never been observed directly. Others have been seen only once, briefly, through a narrow cone of artificial light before disappearing back into darkness. In that context, the question of whether something truly unknown could exist in the deepest parts of the ocean is not speculative in the way popular culture often frames it. It is a question rooted in incomplete data. The Mariana Trench occupies a unique position in this discussion because it combines several factors that limit observation simultaneously. Extreme depth restricts access. Pressure limits the duration and frequency of visits. Darkness removes visual context. And the sheer size of the trench ensures that even multiple expeditions sample only a tiny fraction of the environment. From a scientific standpoint, this combination leaves room for genuine uncertainty. That uncertainty does not automatically imply the presence of dramatic or extraordinary entities. Scientists are careful to distinguish between unknown and unknowable, and between unexplored and impossible. The trench is unexplored in a very literal sense. There are stretches of seafloor where no camera has ever passed. No sensor has recorded conditions directly. No sample has been collected. In those areas, absence of evidence is not evidence of absence. Historically, assumptions about what could exist at extreme depths have been repeatedly overturned. There was a time when scientists believed life could not survive below a few hundred meters. That assumption fell apart as technology improved. Later, it was believed that complex organisms could not exist beyond certain pressure thresholds. That too was revised. Each boundary that seemed firm eventually softened under observation. This pattern encourages caution when making absolute statements. It does not mean that anything is possible. Physics and chemistry still impose constraints. But it does mean that the limits of life, behavior, and structure are broader than once thought. The trench exists at the edge of those limits, where unfamiliar combinations of conditions persist for geological timescales. One area of uncertainty involves biological novelty. Most trench organisms discovered so far belong to known groups. Crustaceans, fish, worms, microbes. They are recognizable even if highly adapted, but recognition does not equate to full understanding. Many species are known from only a handful of specimens. Their life cycles are incomplete. Their behaviors are inferred rather than observed. There is also the issue of scale. Small organisms dominate deep-sea ecosystems, and small organisms are easier to miss. Microbial diversity in the trench is likely vast, yet only a fraction has been characterized. Microbes drive many of the chemical processes that sustain life, but their interactions and capabilities remain largely unexplored. Some scientists suspect that entirely new metabolic pathways may exist in these environments, pathways that operate efficiently under pressure and cold, using chemical gradients that are rare or absent at the surface. Discovering such pathways would not only expand biology, but also reshape understanding of how life can function. Beyond biology, there is uncertainty about physical and chemical phenomena. High pressure alters molecular behavior in ways that are still being studied. Some reactions proceed differently. Some structures stabilize unexpectedly. Under these conditions, materials may form that are unstable elsewhere. Detecting such phenomena requires instruments capable of operating reliably at depth, something that remains technically challenging. Geological processes in the trench also leave room for unknowns. Subduction zones are complex, and much of what happens along them occurs beyond direct observation. Fluids move through rock, stress accumulates unevenly, microfractures form and heal. These processes may produce signals or interactions that have not yet been detected or interpreted correctly. Acoustic data sometimes reveals signals that do not match known categories. In most cases, further analysis links them to distant storms, ice movement, or seismic activity. Occasionally, signals remain ambiguous. Ambiguity does not imply mystery in a sensational sense, but it does indicate gaps in understanding. The human tendency to imagine unknowns often fills these gaps with narrative. Stories of hidden creatures or unexplained phenomena capture attention because they give shape to uncertainty. Scientists generally avoid this framing, not because it is entirely unfounded, but because it obscures the more subtle reality. The unknown in the trench is likely to be incremental rather than dramatic. New interactions, new adaptations, new combinations of familiar elements. That said, there have been moments in deep-sea research where observations genuinely surprised experts. Organisms appearing at depths where they were not expected. Chemical concentrations that did not fit existing models. Behaviors that contradicted assumptions about energy use. These surprises reinforce the idea that the trench still holds unanticipated features. One reason uncertainty persists is methodological. Deep-sea exploration is inherently biased by technology. Cameras illuminate what they point at. Sensors measure what they are designed to detect. Sampling tools collect material of certain sizes and types. Anything outside those parameters remains invisible. This creates blind spots that are difficult to quantify. For example, slow-moving or stationary organisms may blend into the background. Extremely fragile organisms may be destroyed by sampling. Chemical gradients may exist at scales smaller than sensor resolution. The trench environment filters observation in ways that are not always obvious. Time is another limiting factor. Many processes in the trench unfold slowly. Seasonal cycles, if they exist, may span years rather than months. Biological growth can be measured in decades. A single expedition offers only a snapshot. Without long-term monitoring, patterns remain hidden. There is also the possibility that some phenomena occur only under specific conditions. Rare events, transient states, interactions triggered by shifts in pressure, temperature, or chemistry. Capturing these requires either luck or sustained presence, both of which are in short supply at extreme depth. Scientists are aware of these limitations, and they approach claims about the unknown with restraint. The goal is not to speculate wildly, but to identify where uncertainty is greatest and why. In doing so, they often find that the most significant unknowns are not dramatic creatures, but fundamental processes. For instance, the role of deep trenches in global biogeochemical cycles is still being refined. How much carbon is transported downward? How much is transformed? How much returns to the surface through geological pathways? Small uncertainties in these estimates can have large implications over geological timescales. Another area of active inquiry involves resilience. How stable are trench ecosystems? How do they respond to disturbance? Do they recover slowly or not at all? Answering these questions requires understanding baseline conditions that are still being established. The idea that something truly unknown could exist down there is therefore less about the presence of singular anomalies and more about systemic gaps. Unknown interactions, unknown feedback loops, unknown thresholds beyond which behaviour changes. For scientists, this kind of unknown is both motivating and unsettling. Motivating because it represents opportunity for discovery. Unsettling because it highlights the limits of prediction. In environments so far removed from human experience, confidence must always be provisional. This provisionality shapes scientific language. Researchers tend to speak in terms of probability and possibility rather than certainty. They emphasize what is known, but also what remains unclear. This can be misinterpreted as doubt or hesitation, when in fact it reflects rigor. There is also a cultural memory within science. Past overconfidence about the deep ocean has repeatedly been corrected. This history encourages humility. It discourages definitive claims about what cannot exist. At the same time, humility does not mean openness to any idea without evidence. Constraints still matter. Physics still applies. Life, however adaptable, must obey thermodynamics. Materials must obey structural limits. Unknown does not mean unbounded. The trench sits at a boundary where these constraints intersect in unusual ways. That is what makes it scientifically valuable and psychologically unsettling. It is not a blank slate, but it is not fully written either. As technology improves, some unknowns will shrink. Higher resolution mapping will reveal more detail. Better sensors will capture subtler signals. Longer deployments will reveal temporal patterns, yet each advance may also reveal new layers of complexity. This is the paradox that defines deep-sea research. Progress does not necessarily reduce mystery. It often relocates it. Questions evolve rather than disappear. The unknown moves from one scale to another. For scientists working in this field, accepting that reality becomes part of the job. The trench is not a puzzle to be solved completely. It is a system to be approached gradually, with the understanding that some aspects may remain elusive. This acceptance does not diminish the sense of unease. If anything, it deepens it. Knowing that the environment can still surprise even after decades of study, fosters respect tinged with caution. The idea of something truly unknown down there persists not because of fantasy, but because of honest accounting. There are places humans have barely touched, processes we have barely measured, interactions we have barely imagined. As attention shifts from the possibility of unknowns to their implications, another thought emerges. If the trench can challenge assumptions so thoroughly, what does that say about humanity's place in such an environment? How do scientists reconcile their role as observers with the realization that they are profoundly out of place there? There are few moments in science where perspective shifts so completely that it alters not just what researchers study, but how they think about themselves. The deepest parts of the ocean create one of those moments. Standing on the deck of a research vessel, surrounded by instruments, data streams, and years of expertise, scientists can feel confident, even authoritative. But that confidence has a way of thinning when attention turns downward, toward the unseen distance beneath the hull. The Mariana Trench has this effect more consistently than almost any other environment on Earth. It is not simply deep. It is deep in a way that reframes scale entirely. Human bodies, machines, and even institutions feel suddenly provisional when set against a vertical expanse that stretches nearly 11 kilometers downward, governed by forces indifferent to human intention. This feeling of smallness is not metaphorical. It is practical, measurable, and persistent. Every calculation related to trench exploration begins with limits, maximum pressure tolerances, minimum safety margins, battery life measured against descent time, communication delays dictated by physics. From the outset, the environment dictates terms. Scientists are accustomed to working within constraints, but most constraints are negotiable. Instruments can be refined, methods can be optimized, models can be adjusted. In the trench, some constraints are absolute. Pressure will not lessen, darkness will not lift, distance will not shrink. Acknowledging this requires a recalibration of expectations. When crewed submersibles descend, the physical sensation reinforces this awareness. The vehicle becomes a sealed pocket of surface conditions, surrounded by an environment that would destroy its occupants instantly if the barrier failed. The walls of the pressure hull are thick, curved, and deliberately unadorned. There are no windows large enough to forget where you are. Every design choice serves as a reminder of vulnerability. Even uncrewed missions evoke similar feelings. Watching a remotely operated vehicle disappear into darkness on a monitor, operators track depth numbers climbing steadily. There is a point at which the descent becomes abstract. The numbers continue to increase, but the visuals change very little. Darkness looks the same at 2 kilometers as it does at 8. The mind must fill in the rest. This gap between knowledge and perception contributes to the sense of smallness. Scientists know, intellectually, how much water lies above the vehicle. They know the pressure, they know the risks. But there is no sensory reinforcement beyond a few digits on a screen. The scale exists mostly in imagination, and imagination struggles with such extremes. The feeling intensifies when the seafloor finally comes into view. The bottom of the trench does not look dramatic in a cinematic sense. It is often flat, sediment-covered, quiet. The absence of spectacle can be disorienting. After hours of descent through darkness, the destination appears almost mundane. And yet, that very mundanity underscores the enormity of the journey. Standing at the bottom of the world, even indirectly, highlights how thin the layer of human activity truly is. All of human history, culture, and technology unfolds within a narrow band near the surface. The trench exists far below that band, untouched by daily cycles, seasons, or civilizations. It does not acknowledge human presence. This realization has psychological weight. Scientists dedicate their careers to understanding the natural world. They develop expertise, publish findings, and contribute to collective knowledge. The trench reminds them that expertise does not equate to dominance. Understanding a system does not grant control over it. There is also a temporal dimension to this feeling. Geological processes shaping the trench operate over millions of years. Sediments accumulate slowly, plates move imperceptibly, biological adaptations emerge over evolutionary timescales that dwarf human lifespans. In comparison, a research expedition lasting weeks or months feels fleeting. This contrast can be humbling. It places human effort in context, neither diminishing its value nor exaggerating its reach. Scientists often describe a sense of participating in something much larger than themselves, contributing a small piece to a vast ongoing process. The trench also exposes the limits of language. Terms like deep, extreme, and remote lose specificity when pushed beyond familiar ranges. Descriptions become repetitive because the experience resists differentiation. Darkness is darkness. Pressure is pressure. Distance is distance. Words strain to convey what numbers describe, but senses cannot grasp. This linguistic limitation feeds the feeling of smallness. If an environment cannot be fully described or imagined, it cannot be fully possessed mentally. Scientists are trained to communicate findings clearly, yet here they encounter something that resists easy explanation. There is also an ethical dimension to feeling small. Recognizing vulnerability can foster caution and respect. Scientists aware of their limited presence in the trench are often more mindful of impact. Sampling is minimized. Disturbance is considered carefully. The goal shifts from extraction to observation. This shift reflects an understanding that the trench is not a resource to be exploited, but a system to be studied gently. Feeling small encourages restraint. It counters the impulse to treat exploration as conquest. At the same time, smallness can be unsettling, because it challenges narratives of progress. Modern science often celebrates expansion, mastery, and increasing control. The trench resists these themes. Progress here is slow, mastery is partial, control is illusory. For some scientists, this tension is uncomfortable. It contradicts the expectation that knowledge leads inevitably to power. In the trench, knowledge leads instead to appreciation of limits. The emotional response varies. Some researchers find this grounding, others find it disquieting. Both responses are valid. They reflect different ways of integrating awareness of scale into identity. There are moments during trench missions when this awareness becomes acute. A sudden noise, an unexpected sensor reading, a reminder that ascent will take hours. These moments crystallize the reality that there is no quick exit. The surface world feels distant, not just physically but conceptually. Even after returning, the feeling can linger. Scientists report that images of depth stay with them. Numbers take on new meaning. 11 kilometers is no longer an abstract statistic. It is a lived reference point. This lasting impression influences how scientists view other environments. Mountains feel smaller. Oceans feel deeper. The planet feels more layered. The surface becomes one thin slice of a much more complex whole. Feeling small at the bottom of the world also alters how scientists view uncertainty. In many fields, uncertainty is something to be reduced. In trench research, uncertainty is recognized as inherent. Accepting it becomes part of professional maturity. This acceptance does not diminish rigor. It sharpens it. Scientists become careful about claims. They emphasize margins of error. They acknowledge gaps. They resist overgeneralization. The trench, in this way, acts as a corrective. It tempers ambition with humility. It reminds researchers that some systems cannot be rushed, simplified, or fully contained by models. There is also a collective aspect to this feeling. Trench exploration is rarely the work of individuals. It requires teams, institutions, and international collaboration. No single person holds all the expertise required. No single discipline dominates. This collaborative necessity reinforces the sense of smallness at an individual level, but also creates a different kind of largeness. Knowledge becomes distributed. Progress becomes communal. The focus shifts from personal achievement to shared understanding. Scientists often speak of the trench as a place that changes how they think about Earth. It reveals depth not just physically, but conceptually. It shows that the planet's most influential processes often operate out of sight, beyond daily awareness. This perspective can be both sobering and motivating. Sobering because it reveals limits. Motivating because it highlights the value of curiosity, even in the face of those limits. The trench does not diminish human effort by making scientists feel small. It contextualizes it. It places research within a broader framework where significance is measured not by dominance, but by contribution. As scientists continue to work in this environment, they learn to carry that perspective with them. It informs how they ask questions, how they design experiments, and how they interpret results. And as attention gradually turns from human perception back to the trench itself, one final realization emerges. Feeling small is not the end of the story. It is a beginning. It opens space for reflection about why such environments matter, and what it means to engage with them thoughtfully. From here, the focus shifts toward closure, not in the sense of final answers, but in the sense of returning to the surface changed by what has been considered. The trench remains where it is, deep and indifferent. What changes is the perspective of those who study it, carrying forward a quiet understanding shaped by depth, darkness, and scale. Eventually, every descent ends the same way. Slowly, almost reluctantly, the instruments begin their long return upward. Pressure eases in increments too gradual to feel directly. Darkness thins, not all at once, but in layers. The first hint of returning light is subtle, barely noticeable, a faint shift in tone rather than brightness. It takes hours before the surface is reached, and during that time there is space for reflection whether one intends it or not. Coming back from the depths of the Mariana Trench is not just a physical process, it is a mental one. Scientists often find that the return feels different from the descent. On the way down, attention is focused forward, on objectives, systems, numbers, and procedures. On the way back up, there is more quiet. The most difficult part is over, yet the experience lingers, settling into thought. The surface world does not announce itself dramatically when it returns. The ocean looks much the same as it did before. Waves move gently. The horizon stretches wide and familiar, and yet something has shifted. The knowledge of what lies beneath changes how that surface is perceived. Calm water no longer feels shallow. It feels layered, weighted, full of unseen distance. Scientists describe this change in understated ways. They talk about perspective, about scale, about context. Rarely do they frame it as transformation, but the effect is real. After spending time thinking deeply about an environment so far removed from everyday experience, the surface world feels thinner somehow, less complete on its own. Numbers that once felt abstract take on new weight. Depth measurements stop being trivia and start becoming reference points. 11 kilometers is no longer just a record. It is a vertical reality that exists beneath ships, storms, and shipping lanes, quietly shaping the planet while most people go about their lives unaware of it. There is also a lingering awareness of fragility, not just of technology, but of human presence itself. The trench reinforces how narrow the band of conditions is in which humans thrive. A few degrees of temperature, a limited pressure range, access to light and oxygen. Outside that range, survival becomes dependent on artificial support, careful engineering, and constant vigilance. This awareness does not inspire fear so much as respect. The kind that slows decisions, the kind that encourages listening rather than imposing. Scientists returning from trench-focused research often carry this respect into other areas of their work. It influences how they think about ecosystems, climate, and the unintended consequences of human activity. The trench, after all, is not isolated from the rest of the planet. As unsettling as it is to realise, even the deepest parts of the ocean bear traces of surface life. Chemicals sink, plastics drift, sound travels. The idea that there are places entirely untouched by human influence is becoming harder to defend. This realisation adds a layer of responsibility to exploration. Understanding the trench is no longer just about curiosity, it is about stewardship, even when direct interaction is minimal. Knowing that actions at the surface can reach such depths reframes discussions about impact and accountability. There is also a sense of incompleteness that remains. No mission answers everything. No data set feels final. The trench resists closure. Each discovery opens further questions. Each explanation introduces new uncertainties. For scientists accustomed to building toward conclusions, this can be challenging. Yet there is value in that openness. The trench teaches patience. It rewards careful accumulation of knowledge rather than rapid conclusions. It encourages humility in the face of complexity. Coming back to the surface, change does not mean abandoning ambition or curiosity. It means carrying them differently, with fewer assumptions, with greater tolerance for uncertainty, with an understanding that some systems cannot be fully captured by models or measurements alone. The surface world resumes its rhythms quickly. Schedules return. Communications resume their normal pace. The expedition ends. Papers will be written. Data will be analysed. Life continues. But the memory of depth does not vanish as easily. Scientists often report that ordinary environments feel subtly altered after trench work. Standing on land, they are more aware of what lies beneath. Watching waves, they think not just of weather, but of circulation, chemistry, and pressure far below. The planet feels more three-dimensional. This expanded sense of Earth can be grounding. It reminds researchers why exploration matters even when it is difficult, slow, and expensive. Understanding does not always provide comfort, but it provides context, and context shapes better decisions. There is also a quieter outcome, a kind of mental recalibration. Problems that once felt overwhelming may feel smaller by comparison. Others may feel larger, more urgent. The trench has a way of rearranging priorities without offering explicit guidance. As this journey comes to a pause, it's worth returning gently to the present moment, to where you are right now. Perhaps you're listening from a quiet room, or letting these thoughts drift by as the day winds down. Maybe the world around you feels calm. Maybe it feels busy. Either way, beneath it all, the planet continues its slow work, deep and unseen. So let me ask you again, softly this time, where are you listening from tonight? And what time is it in your part of the world? After all this talk of depth, pressure, and permanence, it's grounding to remember the simple markers we still rely on. If you found something calming or thought-provoking in this long descent and return, you're welcome to like the video or subscribe. It helps keep this space going for others who enjoy taking their time with questions that don't have quick answers. The Mariana Trench remains where it has always been, deep, dark, and largely indifferent to human attention. What changes is not the trench, but the way we think about it, and perhaps the way we think about our place on the surface above it. For now, you're here. The ocean is quiet at the top, and it's okay to let the mind rest, knowing that some depths don't need to be solved tonight.